All right, so this unit, we are going to basically be looking at non-conservative forces, all right? So I'm kind of combining sections 9.1 and 9.2 here for the purposes of the notes. They're very, very difficult to separate. So we're going to be working a little bit with what is called the work-energy theorem and work done by non-conservative forces, all right? So here we go. All right, so far, one of the things that we've learned is that if a conservative force does work, that the work done by that conservative force is simply the opposite of the change in potential energy associated with that force. All right, and up until now, largely in Chapter 8, most of the problems we were doing were problems in which our non-conservative forces didn't do any work, and so our total energy was, our change in total energy was zero. And so in my class, we referred to that as being a problem in which energy is conserved, okay? At least within the system, right? And I guess maybe I should probably go on a brief tangent here and say, within the universe, energy is always conserved. But so for the purposes of this class, when I say that, oh, this is a conservation of energy problem, I'm just saying that the total energy at one point is the same as the total energy at another point, right? Okay. Now, this chapter, we're going to learn that that's not necessarily true, and that's because some outside force is either increasing or decreasing the total energy of the object and transferring that energy to some other object, okay, or to some other form of energy. All right. So what we're going to focus on then this chapter is exactly that. What happens if this is not true? All right. And so, well, it turns out that that's true if the work done by non-conservative forces does not equal zero. In English, what if our non-conservative forces do work? Okay. What if our non-conservative forces do work? All right. And so, I've already kind of given away the answer here, right? Our total energy is going to change, right? But before we get there, what we're going to do is we're going to look at what we're going to call our network. And to be honest, I think in most of my answer keys, I wrote network this way. Okay, so these two things both mean, the same thing. All right. So, so let's take a look at network. All right, so here's the deal. So by definition, network it's simply the total of the work done by all of the forces, all right? So maybe we've got, whatever, 3 or 4 forces, right? So our network would be the work done by force number 1, plus the work done by force number 2, plus the work done by force number 3, plus etc., right? Okay. Oh, well, that is, well, let's see, the work done by force number 1 would be, oops, sorry, that's not what I wanted to do. Let's just do it over here. So this is force 1 times our, dot displacement, plus force 2 dot displacement, plus force 3 dot displacement, right? And so it turns out that when you do a dot product, you can factor just like you can with regular multiplication. So if you factor out this displacement vector, then you get which is simply net force dot displacement, right? Okay. So there are 2 ways you can find net work. This is important. I feel like I kind of glossed over this here, but so there are 2 ways you can calculate net work. Option 1 is to add up all of the individual works. Option 2 is to do net force dot displacement. Okay? So, but I think this is a thing that we all already knew. It's a thing that we use a lot. So please make sure that you know this. All right? But we're going to take this one step further to find out something of maybe, I don't know, I don't want to say more useful, but something useful. All right. So let's see. So one of the things that we learned when we learned Newton's laws is that net force is mass times acceleration. So I can write this as net force. I can replace that as mass times acceleration times my displacement. Okay? So, but one of the kinematics equations we learned gives us this. Right? Which means that this is simply that, right? Just multiply both sides by a half. So what I'm going to do is I'm going to replace a delta x with 1/2 vf minus vi squared. So this is m times 1/2 vf squared minus vi squared. Okay, and so what does that give us? Well, almost done here. So if I rearrange and distribute the m, you get 1/2, oh, I guess we're switching to blue, mvf squared minus 1/2 mvi squared. Oh, well that's ke final minus ke initial, which is our change in kinetic energy. Holy moly, we just discovered the work-energy theorem, also sometimes called the work-kinetic energy theorem. All right, here's what we just learned. We learned that the net work on an object, or the net work done to an object, is equal to the change in kinetic energy. Okay? The net work is equal to the change in kinetic energy. This is the work-energy theorem, also sometimes called the that says work, kinetic energy theorem. Okay? Okay. So, like I said a minute ago, so this is sort of, that's the 9.1 video, okay? The 9.2 video is so closely related that I can hardly separate the two. All right, so it turns out that this tells us something about the work done by non-conservative forces. All right, so far here's what we know. From chapter, I guess 7 it was, we know this, right? And just a minute ago we learned this. All right, so let's see. So here's what we know. So remember, net work by definition, well, one way to think about net work is by adding up the work done by all of your forces, right? So one way we can do this is we could classify, right? We could say, all right, well, the net work is, well, that's got to be the sum of the work done by all my conservative forces plus the work done by my non-conservative forces, right? Because every force is either conservative or non-conservative. So my net work is just the sum of those two things, right? Okay, so now let's do a quick substitution. So from here, I know that my network, network equals change in kinetic energy, right? So I know my network is, oh, this is my change in kinetic energy, right? So this is just this, all right? And then from over here, I know that the work done by conservative forces is the opposite of my change in potential energy. So this is negative delta PE plus the work done by my non-conservative forces, right? All right, well, let's solve for this. So to solve for that, I'm just going to add my change in PE to both sides. Well, kinetic energy and potential energy, that's total energy. That's done by the work done by non-conservative forces. Okay? All right, so this whole chapter really, or definitely the first couple parts of this chapter, are really going to revolve around the stuff on this screen right here. Right here, okay? All right, so I feel like I should write this all summarized. All right, so here are the three things we know. We know that our network is equal to our change in kinetic energy. We know that the work done by our non-conservative forces is our change in total energy. And we know that the work done by conservative forces is the opposite of the change in potential energy. Okay? So that is that. So let's do a quick example. All right, so to do this quick example, here's what we're going to do. So suppose I've got a block. It's got a mass of 5 kilograms on it. Okay, got a mass of 5 kilograms, all right? All right, and what I'm going to do, well, so let's start, I guess, by finding our force of gravity. Force of gravity is just 5 times 9.8, so 49 newtons down. All right, so let's suppose that I lift up on this thing. So here's the force of Mr. Hecker. All right, and maybe I exert an upwards force of 60 newtons on it, right? Okay, so what's going to happen there is some of my force is going to go into lifting it, but because I'm producing a net force, some of my force is also going to cause a change in velocity, right? Okay, so let's suppose that I lift it up to a height of, I don't know, we'll do 4 meters. Okay? So I guess there are a couple ways that we can think about this, but I guess I just want to make sure that you guys understand how everything all fits together here. All right, so let's do this. Let's calculate the force done by the work done by the two forces. All right, so the work done by Hecker is the force of Hecker times the displacement, right? So that's 60 newtons times 4 meters, that's 240 joules, right? Okay. And the work done by gravity is the force of gravity times the displacement. So that's negative 49 newtons times 4 meters. So that gives you negative 196 joules, right? Okay. So what does that have to do with all the stuff we just learned? Well, let's see. Let's go one step further. Let's find our... All right, sorry, hemming and hawing. All right, so let's see. So the work done by Hecker, well, that's the only non-conservative force, right? So this statement here is telling me that the work done by my non-conservative forces is 240 joules. That means I gained, that's my change in total energy, right? I gained 240 joules of energy. All right, well, gravity is my conservative force, right? So that means that if the work done by conservative forces is negative 196 joules, then, how do I want to write this? The opposite of that, the work done by my conservative forces, the opposite of that would be 196 joules, right? That's my change in potential energy. All right? Well, so let's think about this. So if I gained 240 joules total, but only 196 went to potential energy, then the remaining 44 joules must have gone to kinetic energy, right? So that means my change in kinetic energy must be 44 joules, right? Right? Because all of my energy gain has to be either potential or kinetic. Okay? All right, well, so let's see. Let's see what just happened there. So we just found our change in kinetic energy. Oh, well, remember, change in kinetic energy is our net work, right? Oh, well, that's the same as net force times displacement, right? So what's my net force here? Well, I got 60 newtons up and 49 newtons down, so my net force is 11 newtons times 4 meters. Aha, 44 joules. So everything works out. All right? Okay, so the idea is we can use these three ideas of work done by conservative forces, work done by non-conservative forces, and net work to solve some pretty complicated problems, okay? And that's sort of what we're going to be exploring in this chapter, is different ways of going about that. All right, now, before I go any further, I got to answer one other question, which is apparently on the next screen. Where does friction fit in all of this? Right, so remember, we know friction is a non-conservative force, right? And to be honest, there's really nothing special about static friction, because when static friction occurs, your object isn't sort of sliding, right? So static friction is just another non-conservative force. All right, but for kinetic friction, one of the things that we are often asked to do is say, all right, well, if your object is moving this way, then kinetic friction is going to be this way, right? So the work done by friction is negative. You're going to lose energy, right? You're going to lose total energy, okay? So, and you know this, if you rub your hands together, your hands get hot, right? Because of friction, okay? So the idea is friction is doing a negative amount of work and you're gaining what's called thermal energy. In other words, heat energy, okay? So many of the questions this chapter are going to ask you about the change in thermal energy for a system, right? So when you rub your hands together, friction's doing a negative amount of work, you're going to gain thermal energy. I kind of wish I'd written a negative sign over here. It doesn't really matter, it's the same thing, right? Okay, but for whatever reason, that just sort of makes more sense, okay? So the work done by friction is the opposite of the change in thermal energy. Friction causes you to lose mechanical energy, you gain thermal energy. Okay, so that is that. So now let's see if we can solve another problem. All right. Okay, so in this example, oh, that's not what I wanted to do. All right, so in this example, we've got this 3 kilogram block down here. All right, and it's going to be launched up an inclined plane by a spring, as shown in the figure here. The plane is inclined at a 30-degree angle. The coefficient of kinetic friction is 0.25, and the spring constant is 800 newtons per meter. So it says if you press the block against the spring to compress the spring 0.2 meters, then how much work are you doing? Okay, well, we got to be careful here, right? Because when you push down on it, there are actually a number of forces. So specifically, there's gravity, right? There's U, there's friction, okay? So let's see if we can't solve this thing, okay? So I think probably the first thing that we want to do is make a free body diagram, okay? So I'm going to kind of gloss over some of this, but so here's what our free body diagram is going to look like. It's a 3 kilogram thing, right? So if you calculate it, it turns out that your FG perpendicular is 25.46 newtons. That means that your normal force is going to be 25.46 newtons. Okay, you're going to have an FG parallel. Pushing it down. That FG parallel is, let's call it negative 14.7 newtons. All right, there's going to be the force of U, which we don't know. And then going uphill, we've got two forces, right? The idea is if you're trying to compress the spring's going to resist that. So there's going to be an upwards force from the spring plus stupid friction. Okay, well, we can at least find our friction, right? Because that's just going to be 0.25 times our normal force. Okay, so the force of friction is 6.37 newtons, right? Okay, but the problem is, so we can't find the force that you're doing because since the force of the spring is changing, that means your force is going to have to change, right? So there's really a lot going on here. Okay, so there's, I guess, a couple ways we can go about this. So let's do this. It doesn't state this explicitly, but the idea is you're going to start, the block is going to both start at rest and end at rest, right? Your goal is you're going to compress the spring and then hold it there, okay? So what that's telling us then is my change in kinetic energy is 0, right? Because it's both starting at rest and ending at rest. So that means that my net work is 0. All right, does that help me any? I guess it doesn't really, because I still have two unknown forces, right? We don't know the force of the spring or the force of U. So because of that, I think I'm going to, instead, let's see if we can figure out something about the change in total energy. Okay, so we've got 2 points. So there's a point here before we've compressed the spring. All right, and then there's the point here after we've compressed the spring, all right? So what do we know? Well, let's see. So in order to talk about energy, we need to choose a point to call a height of 0. So let's call our lowest point here a height of 0, all right? So we're going to call this point Let's call this point B for bottom, and we'll call this, I don't know, S for start. I don't want to use S because I'm going to use R for, relaxed, R, because the spring is relaxed. There we go. I had R in my notes. I couldn't figure out why I used R. Okay. So at point B, what do we know? We know that our GPE is 0, our KE is 0, but we've got elastic potential energy, which we can calculate, right? So our elastic potential energy is going to be half of K times X squared. And so that gives you 16 joules. So that means my total energy at point B is 16 joules. Okay? Now, at point R, to clear up my board a little bit here, I'm already out of room. All right, I'm going to go down a little bit over here. So, all right, now at point R, what do we know? Well, at point R, let's see. It wasn't moving before, right? So the kinetic energy at point R was 0. But we're going to have some GPE, right? So the GPE is going to be the mass of the block, which was 3 times 9.8 times our height. Well, this is a 30, 60, 90 triangle, right? So if this distance here is 0.2 that we squished the spring, that means the height is 0.1 meters, right? Okay, so that gives us 0.3 times 9.8 is 2.94 joules. That jives with my notes. And at that point, the spring is R for relaxed, which means that my EPE is 0, right? Aha, so now my total energy is 0 plus 2.94 is 2.94 joules, right? Okay. So I'm going to erase that and all right, so what do we know? We know that the total energy up here where the spring is relaxed is 2.94 joules. And we know that the total energy down here at the bottom was, what did I say, 16 joules. Aha, so now I can find my change in total energy. All right, so let's see. This is not part B. I'm doing the work here because I didn't give myself enough space. All right, so my change in total energy is the total energy final, which is at the bottom, minus the total energy that I started with, which is when it was at, in its relaxed state. So we ended up at 16 joules after starting with 2.94 joules. So that's 13.06 joules of work done. That is equal to the work done by my non-conservative forces, right? My total energy changed. That tells me how much work was done by my non-conservative forces. Well, let's think. What did work? Well, the work done by non-conservative forces is equal to the work done by friction plus the work done by, how did I label it? The work done by U, I guess. Yeah. The work done by U, right? So let's see. The work done by non-conservative forces, we just found that. That's 13.06. The work done by friction, oh, well, that's the force of friction. Times the distance. And let's see, it's moving down, friction is up, so this is negative, plus the work done by U. Okay, so, come on, computer, work. All right, so, somewhere I have this all written down. All right, so we get 13.06 equals negative 1.274 plus the work done by U. So add the 1.274 and you're going to get, what, 14.6 So the work done by you is 14 point, what's that, 334 or something? I'm doing the math in my head now. All right, so there's the work done by you. Okay, there's a lot going on there, all right? So we have a lot of forces. Some of them are conservative, some of them are non-conservative, all right? So there we go. So that is part A. Yep, all right, and there's my 14 joules. It looks like I rounded to 2 sig figs. All right. Now, B says if you release the block, how far will it go up the ramp before stopping? Do I have time to do this before the bell rings? I don't know. Clear ink, clear ink. Oh, I don't want to clear all of that. Never mind. Okay, sorry. Talking to myself. Shh. All right, so it says if you release the block, how far will it go up the ramp before stopping? So we need a new point here. There we go. All right, so once you let go of it, the only non-conservative force is friction, right? So so let's see. So we decided that when it was at the bottom, the total energy at the bottom was 16 joules, right? All right. So there's going to be some other point up here where it stops, right? So the total energy when it stops is, well, it's just going to be the GPE, right? Which is mgh. So 3 times 9.8 times the height. So let's think here. So the idea is this was up, here's our block at the bottom, right? So it's going to go some distance up the ramp, d, before it stops. And in doing that, the height is going to go from 0 up to some height, h, right? Oh, and remember, this is a 30-degree triangle, right? So this is just 2h, right? Okay, so let's use h as our variable. So that's the only type of energy I'm going to have when I get to my highest point, is just GPE, right? And I know that the work done by friction is equal to the work done by non-conservative forces. That's the same as my change in total energy. That's the same as TE final, which is the total energy when it stops, minus the total energy when it began at the bottom. So here we go. We are just about done here. So the work done by friction, well, we already figured out our force of friction is 6.37 newtons times some distance d, right? And those are in opposite directions, so I can go ahead and tack in a negative sign. So that's the work done by friction. Oh, shoot, but we said that d was 2h, right? So I can make this 2h. And that's got to equal 3 times 9.8 times h minus the total energy at the bottom, which is 16. And then solve that for h. Okay. So I, for some reason, don't have that written down, but we can figure it out pretty quick, right? So let's do this. Let's add 16 to both sides. So I'm going to get 16 equals 3 times 9.8 h plus 6.37 times 2 is what, 12.74? So 3 times 9.8 is 2.94. So you can solve for h, right? So let's see. 16 divided by 2. Sorry for not having this written out. Plus 12.74. I probably could have paused the video, but it gives you about 1 meter, which means that our distance is twice that. Okay. Ooh, which does not at all agree with my answer. Yep, the answer I've printed there is wrong. The answer I just gave you is right. So this should be, if you release it, how far will it go? So it's 2.04 meters up the ramp. Okay. All right. So I think the last thing I'm going to do then is I'd like you guys to, on your own, see what you can do with this guy. All right. Roy pushes a 40-kilogram box up a ramp that's 5 meters long and 3 meters tall. So the length is the hypotenuse. So it's 5 meters long, 3 meters tall. All right. He uses a horizontal force of 700 newtons. Okay. So the block is going to be here. Roy's force is horizontal. Okay. The force of friction is 140 newtons, so I just gave you the force instead of asking you to go through coefficients and whatnot. And so, your force of friction is going to be this way. All right, and so the question is find the velocity of the box when it gets to the top of the ramp. All right, try it out. See what you can do. The answer is right here, 9 meters a second. And if you remind me in class, we can go over it together. All right, there you go. Videos 9.1 and 9.2.